Imagine trying to follow a system where you can be in multiple places at once, take random paths, and still somehow end up with the right answer. Sounds chaotic, right? That's essentially how NFAs, also known as non-deterministic finite automata, work. But what if we could take all that chaos and turn it into something clean, structured, and predictable? Today, my partner Kafui and I are going to show you how to turn an NFA into a DFA, a deterministic finite automata, step by step, using visuals, examples, and even a little bit of Minecraft. I'll let my partner Kafui start us off with the basics.
So first, let's look at the definitions of an NFA and a DFA respectively. So an NFA, or more precisely, non-deterministic finite automation, is a type of machine used in computer science to recognize patterns. I guess what differentiates an NFA from a DFA is the fact that it can move to multiple possible next steps and can even move without reading any input at all, which is what we call epsilon transitions. And a DFA, on the other hand, or more precisely, deterministic finite automation, is more strict. From each state, for every input symbol, there's exactly one possible next state. So it's not possible for you to move to another state using an epsilon. Even though NFAs are more flexible, DFAs are easier for computers to execute. And that is why in this video, we'll be learning how to convert an NFA to an equivalent DFA.
So here we have an NFA constructed for us. Let me walk you through what everything represents. First, let's talk about the input alphabet of this NFA. We'll be using 3 colors to represent different transition functions. The pink arrow represents epsilon transitions, meaning the automata can transition between states without consuming any input symbol. The red arrows represent transitions on the input symbol A, and the blue arrows represent transitions on the input symbol B. Now let's look at the states of the automata. The glowing state, labeled Q0, is both the start state and the accept state. In addition to Q0, we still have 3 other states, Q1, Q2, and Q3. Starting from Q0, there's an epsilon transition to Q1, which means that the automata can move from Q0 to Q1 without reading any input symbol. From Q1, there's 2 possible transitions depending on the input. On input A, the automata remains in Q1 through a self loop, and on input B, the automata transitions to Q2. From Q2, there are multiple possible transitions. On input A, the automata can either stay in Q2 using the self loop or transition back to Q0, which is an accept state. On input B, the automata transitions to Q3. Finally, from Q3, there's a transition on input B that leads us back to Q1, and there's no other outgoing transitions from Q3 for other input symbols. This gives us a clear understanding of how this non-deterministic finite automata operates, including its states, transitions, and how it processes input strings.
To convert an NFA into a DFA, we first need to understand something called the epsilon closure. The epsilon closure of a state is the set of all states we can reach without consuming any input. Let's start with Q0. Since Q0 has an epsilon transition to Q1, the epsilon closure of Q0 is Q0 and Q1, all into bracket. This becomes our starting state in the DFA. So now, instead of working with like individual states, the DFA will work with a set of states. So next, we can then build a transition table. For each set of states, we look at where we can go on input A and B. For example, from the set of states Q0 and Q1, on A, Q1 loops to itself and also goes to Q2. So we get into bracket the states Q1 and Q2. On B, Q1 goes to Q2, so we get Q2. We basically continue this process for each new set we discover, expanding step by step. This table would help us build the DFA.
So let's start building the DFA. Due to the epsilon closure, our start state is going to be a state including both Q0 and Q1. Based on these 2 states, we know that if Q1 consumed an A, it loops back to Q1, and if a B is consumed, we transition to Q2. Since Q0 doesn't consume anything other than an epsilon, we don't have to worry about what other states the automata would be in. Then from Q1, we know that consuming an A would give us a self loop back to Q1, while consuming a B takes us to Q2. Now here's where things start to get a little complicated. From Q2, consuming an A would put us in multiple states. We can either loop back to Q2, transition to Q0, or if we transition to Q0, the epsilon closure would include Q1 as well. From this new combined state, consuming an A would simply loop us back to all the same states, since Q1 only goes to Q1 after consuming an A, and Q2 would just be doing the same thing it just did. If state Q0, 1, and 2 consume the B, we would transition to state Q1, 2, and 3 since Q1 goes to Q2 after consuming a B, Q2 goes to Q3 after consuming a B, and Q0 can transition to Q1 with the epsilon transition. From this state, the only options we have after consuming an A is looping back to Q0, 1, and 2. If we choose to consume a B instead, we would loop back to the same state since Q1 transitions to Q1, Q2 transitions to Q3, and Q3 transitions to Q1. Now let's go back and see what happens when Q2 consumes a B. We can see that Q2 simply transitions to Q3, and the only option Q3 has is to go back to Q1 after consuming a B. We also know that any state that includes a 0 is an accept state. After breaking it down, it's not as complicated as it seems. Now let's go over what we learned today. A DFA is a deterministic finite automata, and an NFA is a non-deterministic finite automata. The main difference between them is that an NFA can have multiple possible paths at the same time due to epsilon transitions, while a DFA can only have one path, making it easier for machines to read. A transition table is a way for us to keep track of what transition function on what state leads up to what state. And finally, we can use a transition table to help us convert an NFA into a DFA. We hope our short video lesson was able to teach you some of this basic information, and now you can build your own DFAs.